Hi guys, Mr. T here, another video. Hopefully that last one helped you out. Just use it for practice, use the exercises in the book to get better and get used to the graphics calculator functions, because it's probably the first year that you're actually using it properly and being shown how to use it. So the next step is actually using exponential equations in real world situations. That's the reason I think why exponential equations are in year 11 is because exponential functions and exponential equations are actually more common in real life than linear equations and functions, because things multiply in certain ways or decay in certain ways. So that's what this last topic here is all about, growth and decay. Because now that we've covered solving exponential equations, you're going to be using solving exponential equations in real life applications. And that's because there's many real world situations where things do not grow or reduce in a linear fashion, or by the same amount each time. So some examples of this, especially populations of animals, but people and bacteria, they usually grow exponentially. That's because when one generation, let's say each generation, one individual can have two, or one parent can have two offspring. So that first generation can have two, but then the next generation, if they've had two offspring, then each of those offspring can have two as well. So that's exponential growth. And then the generation after that, there'll be four offspring, and they could each have two, so there'd be 8. Okay, so that's a example of exponential growth as opposed to linear, where it's growing by the same amount each time. So when one generation reproduces, every member of the next generation can reproduce the same amount, and so on, if not more, in real life. Exponential decay, there's only a couple of examples of that. Radioactive substances and things that depreciate income-wise in value tend to decay exponentially. Alright, so those are a couple of real-world examples of where exponential functions actually apply. So we're going to start off with an example here. It's a population example. An entomologist monitoring grasshopper plague notices that the area affected by grasshoppers is given by the equation A, area in hectares, and this is the function here, 1,000 times by 1.15 to the power of n, where n is the number of weeks after the start of observation. So they're doing an experiment. They're looking at the area that a grasshopper plague covers a certain number of weeks after they start. Okay, so find the original affected area. So these are the questions. Find the original affected area, find the affected area after 5 weeks, after 10 weeks. So these first two, A and B, are just changing what n is. It's referring to the area after a certain number of weeks. It asks you to draw the graph of the affected area over time. I'm just going to get the calculator to do that. You would need to find a way to draw that on your page. I can give you tips on how to do that as well. Basically a substitution, okay? And D, use the graph or technology to find how long it will take for the affected area to reach 8,000. So this is the only one where you're not just substituting into n. This is the one where it says, what is n going to be? How long is it going to take for the area in hectares to be 8,000? Alright, so let's go about, what happened there? Let's go about answering these. So A, find the original affected area. I don't even need the graphics calculator for this right now. Oh, this is frozen. I'll just have it ready to go. The original affected area is going to be when it's been 0 weeks. So basically you're finding I wish there was an easier way to use this funny touchpad. When n is equal to 0. And we have said previously that anything to the power of 0 is equal to 1. And so, formatting, what the heck? Yeah, It's not much of a fan of Word on the Mac. So anything 1,000 times by 1 is going to be 1,000. Sorry about the screen jumping around. Not the ideal video making solution, but you just have to deal with it. Area, therefore, the initial area affected was 1,000 hectares. Why? Because the initial area is when the number of weeks is 0. Anything to the power of 0 is 1. 1 times 1,000 is 1,000. Done. B. Find the affected area after 5 weeks. So that's asking what the area is going to be when it's to the power of 5. Got a calculator here anyway, so let's do that. 1.15 to the power of 5 times that by 1,000. That is going to be 2011.36 to 2 decimal places. Therefore, after 5 weeks, the affected area is 2011.36 to 2 dp hectares. Done. C. Oh, sorry, that was B part 1. I need to number that correctly. B part 2. So now it's asking what the area is going to be after 10 weeks. So the only difference here is you're substituting in 10. What is it doing? So we've got the calculator out. 1.15 to the power of 10 times that by 1,000. That comes to 4045.56 to 2 dp. I literally just pressed backspace there. I don't know why I did that. Therefore, after 10 weeks, the affected area is 4045.56 to 2 dp hectares. That's B answered. C. Draw the graph of the affected area over time. So it's just asking for a graph of that function, which is 1,000 times by 1.15 to the power of n. Now, when you're graphing functions, you're letting this be represented by the y-axis, and you're letting this this variable be the x-axis. So we're going to put that in 1,000 times by 1.15 to the power of, and our variable x is there. Done. Graph it. So what you're going to notice, and if you remember back to some of our exercises previously, the intercept, the y-intercept of this graph is going to be at 1,000. So there's no way you're going to be able to see that there. So what you can do is see if the calculator can find a good fit for it by doing zoom fit. You cannot rely on it though, but it looks like this is going to do fine. Okay, so there's a graph of the affected area over time. So obviously I've got a drawing of this already. Oh. I can just do a dodgy and copy and paste that into there. But you don't have that ability. So you guys are going to have to substitute. So what you can do is substitute in when it's 0, and you already know that that's going to be 1,000. So when x is equal to 0, it's going to be 1,000. So that's your first point. You would be able to graph here at 0, 1,000. So you need to devise some sort of a scale to fit that. Let's say you graphed and you made a scale that went up to like 5 or something. Well, you've already got points here. So really, all you need to do is graph these points. Which is acting all weird for some reason. I'm not going to copy and paste that there. Here you have a starting point where it crosses the y-axis. It's going to cross the y-axis at 1,000 because you've said x is equal to 0 at that point. You could graph this point here, 2011.36, when x is equal to 5. So somewhere around 1, 2, 3, 4, somewhere around there. Then when x is equal to 10, somewhere around there, it's going to be 40, 45.56. So you've got your points anyway. You've gotten the points from the previous questions. Okay, they're probably there to help you out with that. So not too bad. If you do not have previous questions to help you with points, then you just substitute. You don't have to use 5 and 10. You can use 1, 2, 3, whatever you want. You just need more than 1 point to be able to draw this curve, because you have to get a judgment of how curved it is. So that's C. D, use the graph technology to find how long it will take for the affected area to reach 8,000 hectares. Alright, so this is a different one. This is where I actually want to show you how to work it out for real. I literally pressed delete. What the heck was that? D. Yes, this formatting is garbage. So what that's saying for question D, use the graphic technology to find how long it will take for the affected area to reach 8,000 hectares. So this time, we know we're interested in it being 8,000. We just want to know what x is going to be at that point. So, how you've been shown before, how do you solve exponential equations using the calculator? You have to graph both sides. I already have this side graphed. It's in there already, 1,000 times by 1.5 to the power of x. Now, I just need to put the other side in, which was 8,000. Enter. Graph. So, depending on how tall this goes up, we might not be able to see. Yeah, 8,000 is probably off up here somewhere. So, if you can't be bothered zooming yourself, you can go zoom fit and try to get the calculator to work out where to zoom it so it shows the most points of interest. So hopefully, yeah, it looks like it's more gradual here. It's zoomed out a little bit. And hopefully we'll see the straight line of y is equal to 8,000 go across. Okay, so that's not enough because we cannot see. It's going to intersect around here. So now we need to do an extra step, because you can't get the calculator to trace. You can't do second trace and find the intersection if it's not actually on the screen. So you need to work out a zoom setting to make sure that fits. So how do you do that? You go zoom, and then what you can do, no, sorry, it wasn't zoom, it's window. So right now, the calculator thought the best zoom was at Ymax 8,000. Yes, well, that's going to be correct because you need to be able to see y is equal to 8,000. Unfortunately, it's not across enough for us to see where it intersects. There's no point in us seeing negative 10 on the x-axis because we know the intersection is far to the right. Okay, so what we might need to do is extend the x-axis to show 100 instead. So now, instead of the graph where it had the y-axis in the middle before, it's going to show x is equal to 0 right on the left side, and it's going to go up to 100 on the x scale. So hopefully now we'll be able to see where they intersect on the screen at some point. So it's drawn the curve. Come on. And now it's drawn the 8,000 line there. So the intersection is definitely on the screen, so I can go second trace, intersect, first curve, second curve, guess. Right, bam. So that's told me therefore x equals 14.88 to 2 dp when affected area is 8,000. And so we need to interpret that as well, because x in this case is representing number of weeks after observation. Therefore, the affected area is 8,000 hectares after 14.88 weeks. Okay, so that's the solution to the first one here. Might resize that so I can fit all the... Why doesn't it go up there? Okay, there we go. Now that's done. Now we'll do a decay example and I'll be done on this video. Okay. So this is the opposite. Instead of a graph curving up like that, up and to the right, a decay is where it curves down and to the right. So in this case, when a diesel electric generator is switched off, the current dies away according to the formula blah blah blah, where time is the time in seconds after the power is cut. What current flowed in the generator at the instant it was switched off? So at the instant it was switched off, our time would have been at 0. So we are just doing a substitution for time when it's 0. Anything to the power of 0 is 1. So the current is going to be 24 amps. Therefore, at the instant the generator was switched off, the current was 24 amps. B. Find the current when time was 1, 2, and 3. Okay, substitutions again. So we need to substitute when it was 1. We need to substitute when it was 2. This is all calculated jobbies. When it was 3. So I leave more space between. So using this, 0.25 to the power of 1 times by 24 is going to be 6. At 1 second, current will be 6 amps. As you can see, I'm working out there. Second one, 0.25 to the power of 2 this time. 0.0625 times by 24, 1.5 at 2 seconds. Current will be 1.5 amps. Lastly, at 3 seconds, where we substituted 3 into whatever x is, 0.25 to the power of 3 times by 24. At 3 seconds, current will be 0.375 amps. Boom, that's those first two questions answered. C. Plot the graph of I against t for time is greater than 0 seconds using the information above. So as we've seen before, how do you plot graphs? You use this function, the y equals function. And so the function this time is 24 times by 0.25 to the power of x. So 24 times by 0.25 to the power of the x variable. Graph, and what you're going to notice is it's going to remain with the last zooming setting. Can't see anything, useless. So you go to zoom and set it to zoom standard. See if you can see anything now. There we go. And all you notice, because it's of this particular form, we don't actually need the negative side. So what you can actually do is go to window and make it start from 0. Start from 0 instead. You get a nicer graph that way. So there's my graph. Unlike you, I get to screenshot this. So that's how I'm going to answer it. However, if you wanted to draw that in your book, you would be using these points from before. Okay, so you know that at time 0, it's going to be at 24, so it's going to cross the y-axis at 24. I might actually change this to show that. So I'll set the y-axis to start at 30. How about that? There. So 24 is going to be about there. So you have 1 point on your graph. Then you can have another point at 1 second. From part B, the first answer, at 1 second it's going to be at 6. So you're going to have a nice little point there at 1 6. At time 2, it's going to be at 1.5 amps, so 2 1, another point there, and you can even use this third point here. At time 3, it's almost at 0, really low. So you have your points here to draw your graph in your book. And now, quickly do the last little bit. Use the graph technology to find how long it takes for the current to reach 4 amps. So we're trying to work out, we're using this function again. But this time, we know we're interested in 4 amps. We want to work out how long it takes to get to 4 amps. So the way we've solved these all before is to graph both sides. That side is already graphed, 24 times by 0.25 to the t. Now we just need to put y is equal to 4 on the other side. Graph that. We've set it up already so that the intersection is visible. So now all we need to do is go second trace, find the intersection for me please, first curve, second curve, guess. So what is that telling me? Current is at 4 amps when time is 1.2924 blah 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 2 dp seconds after when the generator is switched off, after generator is switched off. So that is another example, this time solving a decay question. That's a big video, but it covers everything you need for the last little part of this topic. Hopefully it helps you out, and I'll see you in the next video.